Well, hello there. Today we're going to learn about functions and relations. We're going to start chapter 1 today, and that's our first section, relations and functions. So we're going to start off with some definitions. First is that a relation is a pairing of input values with output values. So some type of x with some type of y value. Pretty much everything we do in math is a relation. There's some type of pattern or relationship between the inputs and outputs. But now a function is a more specific type of a relation. So a function is a relation where each input is paired up with exactly one output. Another name for the output is the dependent variable, and another name for the input is the independent variable. And we talked about that in science class. We also talked about that in class earlier. One way you can think about these is that every function is a relation, but not every relation is a function. Kind of like that good old every square is a rectangle, but not every rectangle is a square. Alright, continuing on. Example 1, determine if the relation is a function. Explain your reasoning. Remember, we want each input to be paired up with exactly one output. So if we look at letter A, we have a table of the inputs and outputs, or the x's and the y's. And if we look, each input, there's different inputs, they're all different inputs, and they all have an output. Since each of those inputs has one output, then it is a function. Yes, each input has only one output. If we look at part B, we have a graph. And this is not a function because all these positive inputs, this 1, 2, 3, 4, and the decimals in between have two outputs. So for example, this input of 3 has an output up here and an output down here, making it not a function. Because that output of 3 has two outputs. So that input of 3 has two outputs. Then if we look at letter C, here we have a listing of numbers and ordered pairs. But if you notice, each of those ordered pairs has a 3 as the input. And they all have different outputs. So this is not a function because the input of 3 has multiple different outputs. If we look at letter D, again we have a table. Looks similar to A, but now the trick is that we have the same input twice. We have the input of -1 and another input of -1 here. And in this case, they have two separately different outputs. So this is not a function because the input of -1 has two different outputs. Look at letter E. We have a straight line graph. And if you notice, each of these x values has only one y value. This x of -4 has one y down here. This x of 0 has a y up here. This x of 2 has a y up here. Each of those x's has only one y, or each input has only one output. Again, we have a list of ordered pairs. Here we have all different inputs, and so as long as all those inputs are different, each input has only one output. So that is a function. Continuing on with letter G, the relationship between students in a class and their assigned seats. Well, if you think about this, how many seats did you get in this class? You only have one assigned seat. So therefore, it is a function. Each student is the input, has only one assigned seat, which is the output. And then our last example is H, a relation where the inputs are the number of state representatives and the output is the number of state senators. So every state has 2 state senators, but the state representatives can have a different number depending on which state you're in. So this is a function Each input has only one output. It just so happens in this case all the outputs will be 2. But that's okay since none of the inputs have more than one output. So for example, let's just say we have a state that has 7 representatives. They have 2 state senators no matter what. Again, the representatives depends on the population. We have another different state that has 6 representatives, but you always have 2 state senators. Even if we have another state that has 6 representatives, it still has 2 state senators, and this point 6,2 just happens to be the same point, so it's not a different point, therefore it's still a function. Alright, flipping on to the next page. We have the vertical line test. So first thing you want to do is plot these points and make a line. So now if you have them graphed, I connected the points for the first one and not for the second one. It didn't matter if you connected or not. Step 2 says draw a vertical line through each point. So I'm going to draw a vertical line here, vertical line there, going through each point that we plotted. And then I'm also going to do it on the second one. Just like that. Alright, what does this tell us about each relation? What it tells us by us drawing the vertical lines, it tells us the number of outputs for each input. So if we look at this first graph, each of those inputs has only one output. This input of -4 has only one output because it's only crossing at one spot. This input of 2 has only one output because it's only crossing that vertical line at one spot. Whereas on the second one, that first point, x value of -2 has only one output of 3, but this input of -1 has 2 outputs. That vertical line is crossing at 2 spots. It has an output of 3 and 2, making this one not a function. So what we learned from that is the vertical line test. And the vertical line test says, if a vertical line intersects the graph of a relation in more than one spot, then the relation is not a function. So therefore, since the vertical lines cross the graph at only one spot, the first graph is a function. Where on the second, this vertical line crosses the graph in 2 spots, so this one's not a function. Alright, example 2, we're just using that idea. We look at the first graph, and I start to draw vertical lines. If you notice, all these vertical lines only cross the graph at one spot. Therefore, the first one is a function. Where on the second graph, if I draw vertical lines, although the graph only touches the line only touches the graph at one spot here, if I draw a vertical line at that spot, this makes it not a function. Alright, on to 1-2. And now we're looking at the notation for functions. So the notation for functions is we use the symbol f parenthesis x to denote a function. Now the way we read this is the value of x, f of x, or oftentimes we'll just say f of x. F of x does not mean f times x. It's just notation. F is the name of it. We'll use other letters. We'll use G. We'll use H. We could call it John of x if we wanted to. We could call it Kenny of x. Whatever. That f is just a name, so that changes. When the equation is written in function notation, f of x denotes the output. And again, the output is the dependent variable of the function, and the x is the input or the independent variable. Alright, here's some examples. Identify the input and output in each equation, then write each of the variables as an ordered pair. So remember, output or x is always comes first in the ordered pair. Input's always first, output's always second. Alright, so if we look at this first one, we have f of x equals 3x minus 2. The x is your input. Our output is the f of x. Now, whenever we write ordered pairs, input always comes first, so x goes here, f of x is our second value. We have a little bit different notation for letter B. We have y equals x squared plus 7, which is what you're used to. Here our input is x, our output's y, and then our point is xy. So therefore, f of x and y really mean the same thing, so they'll be interchanged a lot. And then as we look at letter C, it says s of t equals t times t minus the quantity of t minus 3. Notice we have different notations. Now, whatever's inside your parentheses is always your input. So in this case, our input is the t, because the t is inside the parentheses in that notation. And then whatever's outside is your name, which is the output. So s of t is the output. And then we write that as an ordered pair, t comma s of t. When we evaluate these functions, we just follow these steps. We're going to evaluate the function f of x equals 3x minus 2 at x equals 5. In other words, find what f of 5 is equal to. Step 1, whenever you're asked to find f of 5, or f of anything, or each of anything, you always replace each x with that number. In this case, we're replacing the x with the 5, because we want f of 5. So notice the 5 went in here for the x. This is just notation saying we're putting a 5 into the f function. And then we also replace the x on this side with a 5. And now what this becomes is a PEMDAS problem. We're going to use the order of operations to simplify the right side of the equation. We never touch the left-hand side. The left-hand side is a notation saying we're putting a 5 into the f function. So I'm using PEMDAS at the multiply first, so I end up with f of 5 equals 15 minus 2. And then I just simplify that again. 15 minus 2 is 13. And then make sure you write this function notation. Your final answer is f of 5 equals 13. That means the input is 5, the output is 13, or this means that the point 5, 13 is on the graph of the function. Alright, you can work on your homework, which is pages 4 and 5.